Okay, guys, I want to finish up about talking about comparing means with a very, very important kind of cautionary tale. Ooh. And this cautionary tale is to do with the types of things you're comparing and the types of samples you're comparing. So if you remember back the previous little movie that we made, we were comparing petal lengths or some kind of characteristic of flowers. And there was no reason that you could pair one number for one sample with another number in another sample in a natural way. There was no reason to associate one number in one sample with another number in the other sample. Now there are situations, and sometimes they're very important situations, and they're very important that you identify these situations where you can do this. And when you can naturally pair numbers in two distinct samples, you have what are called dependent samples. And the test for dependent samples is essentially the same test in R, but from a statistical point of view, it's fundamentally different. Okay, so let's assume, so if you, and the classic example of dependent samples, folks, and the ones I'm going to use is to do with twins and to do with identical twins. Suppose you were looking at a response of a drug. So you would give one twin the control, placebo, and another twin the actual new drug or the drug itself, and you would compare the responses. Because the reason why this is so good from a pharmaceutical point of view is that all the other effects you're eliminating. The only thing that's being tested here is the efficacy of the drug. Okay, so that's the classical example, and that's the example we're going to use as well. We're going to use the example of two twins separated at birth. This is bizarre, I know. And we're going to test to see if the IQ of the twins depends on how they were reared. So apparently, now I'm not sure if this data set is apocryphal or not, but apparently there is this data set that I've sent you. Now, in Loop. Now in Loop, I saved the file as a CSV file, but my stupid Mac then is put it into Numbers format. Numbers is the Excel for Mac. Now hopefully you're able to read that and convert it into a CSV file so you can use the file that I put up in R, the file I put up in Loop in R. So I've put up a data set there, and basically they're the results of IQ tests on twins, one of whom was raised by their natural parents and the other twin raised by non-biological parents. I know that this is bizarre, but apparently it's true. And we want to see if if the environment has an effect on IQ. That's basically the test. Now, in the notes on Loop, I show you that the important variable when you're comparing dependent samples is the difference between the paired numbers. Now remember, for dependent samples, there is a natural pairing involved between samples. Okay, so when you're looking at dependent samples, it's the difference in values that's the most fundamental quantity. So what you do is you get the difference between each pair of numbers, and you do a statistical test on the differences between the paired numbers in the two samples. And you get a confidence interval for the difference, and you see what it is. Okay. Now I went through this, what you do in statistics in the Loop notes, but from a practical point of view, folks, you really don't care about what's going on in the background, because we now have R, so we can use R to do the test without really understanding in any way, really, which is a bit dubious, of what's going on statistically. Okay. So I'm going to look at the twins data, as I say, guys, and show you how to test and why it's important to recognize when you have paired samples. Okay, so I'm going to, sorry guys, I'm going to come down here. I've saved the twins data as twins.csv. Okay. And if I see what's in TD, because I know it's not a very big file, I get this response here. So this is what you should be able to load into R. Now again, guys, I'm not sure if you're able to do that because, as I say, my stupid Mac there doesn't seem to be a way of unformatting even CSV files on the Mac. It's just bizarre. But hopefully you're able to download this data anyway. So this is the two sets of twins, or not, there's one set of twins. No, there's not. There's 32 sets of identical twins, and here are the IQ scores. Okay, and we want to see if I think twin one is raised by biological parents, and twin two is raised by non-biological parents, and we want to see if there's a difference between the IQ scores. I know this is very kind of very Nazi kind of eugenics kind of a thing going on here, but let's just do this as an example. Okay. Now, the way you do it, we've got two samples here. We want to see if there's a difference in the mean response between the two samples. You do exactly the same in OR. It's exactly the same test. I'm calling this TD. So we're going to TD dot, the name of it is twin1, is the first column. Okay, now here's the difference. Now, if I just did this, folks, you get what we did before, and you get an estimate then for the 95% confidence interval in the difference in the means. And you see it's minus 10 to 4.35. But that's not what we have here. The t-dot test as the basic t-dot-t test, the basic t-dot test is for independent samples. If you have dependent samples, you have to add something. And it's very simple. So what you do is you just write paired equals true. Okay, so because you know that the samples are not independent, they're dependent samples, and you want OR to take account of that. And when you do that, folks, you get a significantly different 95% confidence interval. Okay, so it's minus 6.1 to 0.3. Okay? And that's a very, very important little thing to remember. And being able to identify when two samples are dependent is usually fairly straightforward, but you need to keep it in your mind when you're doing this type of analysis. First question you ask yourself is, are the samples dependent or independent? And it, as I say, as you can see here, guys, the confidence intervals that you get are significantly different. They really are different. Okay. In here, we know that the samples are paired or twinned, or their samples are dependent. And if you look at the confidence interval you get, then it's minus 6.1 to 0.3. Now, the important number, as in independent sample analysis, is the number 0. If 0 is in the confidence interval, then we can say that we essentially don't, we can say that the mean response could be the same. So in this context, it doesn't matter whether the twins were raised by their biological parents or by their non-biological parents, because 0 is in the confidence interval. Okay? And that's fair enough. Now, I'm going to show you now how you can maybe lie with statistics and how really statistics, there's something very dubious going on here. But let me just say, this is the context of, recent controversies about the drug, the vaccine response for COVID-19. There's been dubious kind of statistics going on. So let me show you how you can actually manipulate statistics here. In this context, I've just done the usual t-dot test, and I've made sure that they were paired, and I got this response. I see that 0 is in the confidence interval. So my assertion is that they're at 94. We're 95% sure that the mean was that at 95% confidence, you cannot say if there is a difference between the two methods of raising children. Okay, of raising twins. Okay, so let me just switch that around. Let me just change the confidence interval. Now, I'm changing the confidence interval to 0.9. Now, if you change the confidence interval to 9, so 90%, you see that the 90% confidence interval, folks, is minus 5.57 to minus 0.24. 0 is not in that confidence interval. And so what this is telling you is that there is a difference between twins being raised by their biological parents or their non-biological parents. And so nurture is important. This is the nature versus nurture debate. Okay, so all I've done here, guys, is I've changed the confidence interval. I'm getting a completely different answer. Okay, so what this is telling you is that you're 90% sure that there is a difference in twins being raised by their biological parents and their non-biological parents. But if you go back up there on the screen there, you're not 95% sure of that. You are 90% sure, but you're not 95% sure. So it depends on how certain you want to be. And people manipulate, or they just quote statistics that suits their ends, or that suits their hypothesis, or this suits their prejudice. Okay, if you really believe that's important that that people be raised by their biological parents as opposed to their non-biological parents, then you would say that you would do this test and show that you're 90% sure that there is a difference. Okay. But if you go up to 95%, you're not 95% sure. So this is a little bit esoteric and a little bit confusing. I do accept that. But and from your perspective, guys, it's not really that important, because what I'll ask you to do in this little test we're going to have next week is I might give you some kind of two samples and ask you to do a t test. And all you have to remember is to in your own minds to be sure if the samples are dependent or independent. Okay, so because if they're dependent, you have to augment your t.test function in OR with the paired equal to true argument. I would probably give you the confidence level as well. If I don't tell you what the confidence level is, 95% is fine. Okay. Now, before I finish this, guys, I just want to tell you that I'm also on Loop. I'm going to put up a little problem set for next week where we talk about the problems that arise when you have small samples. Now, up to now, for both dependent and independent samples, the sample sizes were big. And traditionally in statistics, big samples are samples which are greater than or equal to 30. Okay? But really, you should have more than that. But that's the kind of the rock bottom number is greater than or equal to 30 are big samples. Typically in engineering, though, because tests sometimes are very expensive and tests are destructive, you can't get that many samples. But you still want to get some information. So when you have small samples, the two tests essentially are the same if the samples are dependent and independent. But what you have to make sure is that the samples are taken from a normal distribution. So you have to use the QQ norm and the QQ line test before you do the t.test in OR. And that's the only kind of difference really between small samples and big samples. When you have small samples, you must test for normality. You must test that both samples are normally distributed when the samples are independent, and you must test that the difference between the values in the samples are normally distributed when the samples are dependent. And we'll do an example in the notes or in next week's tutorial. I will put this tutorial question up hopefully the end of this week, and you can have a go of it during the week. Okay, so I'm going to end this here. It's a very, very straightforward thing here, folks. In OR, it's very, very straightforward how to testing dependent samples. It's and because OR does it for you, and there's an awful lot of statistics going on in the background here, which really you don't have to worry about. What's crucial, as I say, is identifying if samples are dependent or independent. Okay, so I'm going to end it here, and I'll talk to you tomorrow because I've recorded this on Tuesday, a tutorial tomorrow. Okay.